Hello viewers, in today's class we are going to discuss one important property connecting the Dirac delta function with its derivative, right? So in this lecture we'll prove this important property of Dirac delta function, that is x square times the second derivative of Dirac delta function is equal to 2 times the Dirac delta function itself, right? So let us start. So viewers, to prove this property, let us start with the definition of Dirac delta function, right? Now see, we know that the Dirac delta function is defined by this integral that is minus infinity to infinity, and here we have f of x and delta of x minus a dx is equal to f of a, right? So the Dirac delta function at the point x is equal to a is defined by this expression, right? And we can also define the Dirac delta function by this integral, that is minus infinity to infinity, and here we have delta of x dx is equal to 1, right? So this expression or this integral shows that the total area bounded by the Dirac delta function in the neighborhood of x is equal to 0 is 1, that is a unity, right? So to prove this property, will make use of one important property of Dirac delta function, right? So we know that if we have this integral that is minus infinity to infinity, and here we have some function f of x, and here we have the nth derivative of Dirac delta function, then this integral is equal to minus 1 raised to n, and here we have the nth derivative of this function on which the Dirac delta function acts is f of n, and here we have x, and we calculate the value of the nth derivative of f at x is equal to this point, that is a, right? So this is an important property of Dirac delta function involving the nth derivative of Dirac delta function at that point, that is x is equal to a, right? So we'll make use of this property to prove this one, right? So now we'll start with the integral, that is I is equal to minus infinity to infinity, and here we have some function f of x, and here we take the second derivative of Dirac delta function at some point x is equal to a, right? So to prove this property, we'll start with this integral, right? So here we have the second derivative, so here we have the double prime, so the double prime indicates the second derivative of delta function, and here we have the nth derivative of Dirac delta function, right? So what we have done here, we have taken n is equal to 2, right? So in this expression we have taken n is equal to 2, right? So now if we apply this property to this function f of x, then we have minus 1 raised to n, right? So n is 2 because the second derivative involves here, so here we have 2, and then we have the second derivative of this function at x is equal to a, right? So here we have x is equal to a. So now we can see that minus 1 square is positive. So we are left with the second derivative of f at x is equal to a, right? So now see, here we have x square times the second derivative of Dirac delta function in the left hand side, right? So what we will do, let us replace this function f of x by x square, right? So f of x is replaced by x square, so that we get x square times the second derivative of Dirac delta function at x is equal to a, right? Further we can replace this a by 0, right? So once we make these changes in this integral, then see, this integral I reduces to minus infinity to infinity. For f of x we have x square, and here we have the second derivative of Dirac delta function at x is equal to a 0, so we have x minus 0, which is simply x, right? So now we have this term, that is x square times the second derivative of Dirac delta function. So now this expression is equal to this one, right? That is the second derivative of f of x at x is equal to 0, right? So the second derivative of x at x is equal to 0, because a is equal to 0, right? And our f of x is x square. So let us find the second derivative of f of x. So f prime of x is equal to 2x, because the derivative of x square is 2x, and then the second derivative of 2x is simply 2, because the derivative of x is 1, right? So we can now replace the second derivative of f of x by 2. So here we have 2, which is evaluated at x is equal to 0. So this is simply is equal to 2, right? So we see that we have this integral minus infinity to infinity. Here we have x square and the second derivative of Dirac delta function, that is equal to 2, right? And now to get this term, we'll make use of this definition of Dirac delta function, right? So viewers, see, we have this expression, right? And here we can write minus infinity to infinity x square, the second derivative of Dirac delta function, and this 2 may be written as 2 times 1, right? And this one can be replaced by this integral, right? So we can now write 2 times the integral minus infinity to infinity. Here we have delta of x dx, right? Now if we take this 2 inside the integral sign, we have integral minus infinity to infinity, and here we have 2 times delta of x dx, right? So now if we compare this integral with this one, then we can see that this expression is equal to this expression, right? So comparing these two integrals, we have x square times the second derivative of Dirac delta function is equal to 2 times delta of x, right? So this is how we can prove this important property of Dirac delta function, connecting the Dirac delta function with its second derivative. Hello viewers, in today's class we are going to discuss two important problems related to Dirac delta function, right? So here in this lecture we'll calculate the value of these two expressions involving the Dirac delta function, right? And we'll see the properties which will be used to find out the values of these two expressions involving Dirac delta function, right? So let us start. So now let us take the first expression, right? So here we have a function 3 times cos square 3x plus 2 sine x over 2, and here we have delta of x minus pi, right? So to find out the value of this expression, let us take this function as f of x, right? So if we take this function as f of x, and this Dirac delta function as delta of x minus a, where a is pi. So this expression then takes the form f of x delta of x minus a, right? Where f of x is this expression and a is pi, right? So now we know an important relation in Dirac delta function, and the relation is f of x delta of x minus a is equal to f of a times delta of x minus a, right? So this is an important relation in Dirac delta function. So f of x delta of x minus a is equal to f of a delta of x minus a, right? So here what we have done, we have evaluated the value of this function f of x at the point x is equal to a, right? So here f of x delta of x minus a is simply f of a delta of x minus a. So we can now find out the value of f of a, and f this a is pi, so we have f of pi, and here we have delta of x minus pi, because we have assumed that a is equal to pi, right? So f of pi is given by substituting x is equal to pi in this function. So we have 3 cos square 3 pi plus 2 times sine pi by 2, and here we have simply delta of x minus pi, right? So now the value of cos 3 pi can be calculated by this relation from trigonometry, that is cos of k pi is equal to minus 1 raised to k, right? So here the value of k is 3. So we have cos of 3 pi is equal to minus 1 raised to 3, that is equal to minus 1, right? So k is some integer, right? So cos 3 pi is equal to minus 1. So here 3 is an odd number, so cos 3 pi is minus 1, right? And the value of sine pi by 2 is equal to 1, right? So we can now take or substitute the values here. So we have 3 times minus 1 raised to 2, and here we have 2 times 1, right? And here we have delta of x minus pi. So this is minus 1 square is 1, so we have simply 3. This is 3 plus 2 delta of x minus pi, so this is 5 times delta of x minus pi, right? So the value of this expression is equal to 5 times delta x minus pi, right? And always remember that to calculate the value of these kind of expressions, we can use this relation. Now let us take the second problem, right? So here we have x square minus 5x plus 3 and delta of 3 times x minus 4. So what we will do here, here also we will apply two important relations from Dirac delta function, right? So the first one is the relation which we have used in solving the first problem here. So f of x delta of x minus a is equal to f of a delta of x minus a, right? So this will be the first relation, and then we'll make use of this important uh, property of Dirac delta function, that is delta of ax is equal to 1 over the absolute value of a, and here we have delta of x, right, where a is not equal to 0, right. So see, here we have delta of 3 times x minus 4. So here we can slightly modify this property to delta of, say, lambda times x minus a is given by 1 over absolute value of lambda, and here we have delta of lambda times x minus, here we have simply delta of x minus a, right. So we have modified this property to this one, and here also lambda is not equal to 0, right. So these two properties will be used to get the value of this expression, right. So here this function can be assumed to be f of x, and here we have delta of 3 times x minus 4. So the value of lambda is equal to 3, and the value of a is equal to 4, right. So now this expression can be written as f of x, then we have delta of lambda times x minus a, right? So using this property, we can now write f of x and 1 over that is absolute value of lambda delta of x minus a, and this is 1 over absolute value of lambda f of x, and here we have delta of x minus a, right, and f of x delta of x minus a can be replaced by f of a delta of x minus a, right. So we can have here 1 over mod of lambda, and here we have f of a. Using this property, f of x is now replaced by f of a, and here we have delta of x minus a, right. Now see, lambda is 3, so we have mod of 3. So mod of 3 is simply 3. So we have 1 over 3, and f of a is f of a is our 4. So here we have f of 4 and delta of x minus 4, right. So now we need to find out the value of f of 4. So now f of 4 can be obtained by taking x is equal to 4 in this expression, right? So f of 4 is 4 square, then we have minus 5 times 4 plus 3. So this is 16 minus 20 plus 3. So this is 16 minus 20 minus 4, and this is 3, and this is minus 1, right. So this f of 4 may be replaced by minus 1. So we have now the value of this expression is equal to 1 over 3 times minus 1. Then we have delta of x minus 4, right. So this is minus 1 over 3 delta of x minus 4, right. So the value of this expression is equal to minus 1 over 3 delta of x minus 4. Hello viewers, in today's class we are going to discuss one important problem from Dirac Delta function, right? So in our earlier videos we have already discussed a lot about Dirac Delta function, right? So in this class we'll evaluate this integral involving the Dirac Delta function. So here we have the integral minus infinity to infinity, and we have e raised to minus x square delta of x square minus 1 dx, right. And here we see that we have a function e raised to minus x square associated with this Dirac delta function, right. And e raised to minus x square is the well-known Gaussian function, right. So let us start. So viewers, here what we will do, right? See, here we have a quadratic function inside the Dirac delta function notation, right? So what we will do, we'll take this quadratic function as f of x, right? So we have f of x is equal to x square minus 1, and let us take this function as g of x, right? And g of x is the Gaussian function, that is e raised to minus x square. So now our integral, it can be written as minus infinity to infinity, and here we have g of x, and here we have delta of f of x and dx, right? So now to move further, we'll make use of an important property of Dirac delta function. So we know that if we have a function f of x, that is, if we have delta of f of x, then delta of f of x can be written as sigma and 1 over the absolute value of f prime of x of I, and here we have delta of x minus x of I, right? So this is an important property related to a Dirac delta function. So we'll also elaborate this property when we solve this integral. So now see, here we have some function f of x, right? And if we need to find out the delta of f of x, then delta of f of x can be written as summation, and here we have 1 over mod of f prime of x of I delta of x minus xi, right? So here xi are the roots of xi are the roots of or the solutions of the equation f of x is equal to 0, right? So here we have this function f of x, so we'll take f of x is equal to 0 and we'll form an equation, right? And xi, this xi are the roots of this equation f of x is equal to 0, right? And after finding out the solutions of f of x is equal to 0, we find the derivative of this function f of x, that is f prime of x, right? And then we calculate this derivative at these points, right? So we'll find out f prime of x of I, right? And then we calculate this quantity, that is 1 over mod of f prime of xi, and then we'll use this summation sign. So let us see how we can apply this property to this integral. Now see here, f of x is x square minus 1. So we will form an equation f of x is equal to 0, and that is x square minus 1 is equal to 0, right? So x square is equal to 1. So x is square root of 1. So x is now equal to plus minus 1, right? So we have two solutions of this equation. So the first solution is x1, that is equal to plus 1, and the second solution is x2, that is minus 1, right? So here we have two solutions of f of x is equal to 0, right? So in this summation sign, we'll go from I is equal to 1 to 2, right? And let us now find out the derivative of f of x, right? So f prime of x is d by dx of x square minus 1. So this is 2x, because the derivative of x square is 2x and the derivative of 1 is 0, being a constant, right? So we have f prime of x is equal to 2x. So now let us find out the quantity, that is mod of f prime of x1 and then f prime of x2, right? So f prime of x1 is mod of f prime of plus 1, and then here a mod of f prime of x2 is the mod of f prime of minus 1. So here a mod of f prime of 1, right? So when we take x is equal to 1 in this expression, then we have mod of 2 times 1, that is equal to mod of 2, that is simply 2, right? And when we find mod of f prime of minus 1, then we take x is equal to minus 1 in this expression. So we have 2 times minus 1, that is mod of minus 2. So this is simply 2, right? So now this property can be written as delta of f of x, and now the value of I goes from 1 to 2, right? So here I has two values because here we have two roots, right? x1 and x2. So we can now write 1 over mod of f prime of x1, and here we have delta of x minus x1, then plus, due to this summation sign, we have 1 over mod of f prime of x2, and here we have delta of x minus x2, right? So substituting the value of x1 and x2, we have mod of f prime of plus 1. Here we have delta of x minus 1, and here we have 1 over mod f prime of x2. x2 is minus 1, and here we have delta of x plus 1 because x2 is minus 1. So minus and minus becomes plus, right? And mod of f prime of 1 is given by 2. So here we have 2 delta of x minus 1, and here also we have mod of f prime of minus 1 is 2, and here we have delta of x plus 1, right? So now we can write it as half, taking half common. So we have delta of x minus 1 plus delta of x plus 1, right? So now delta of f of x. So f of x is x square minus 1, right? So delta of x square minus 1 is half delta of x minus 1 plus delta of x plus 1. So now this integral I can be written as minus infinity to infinity. G of x is e raised to minus x square, and for delta of f of x, we have this expression. So we can take half common here, and we have delta of x minus 1 plus delta of x plus 1, and here we have dx, right? Now taking half outside the integral, we have half, then we have minus infinity to infinity, and we can write here two integrals. The first one is e raised to minus x square delta of x minus 1 plus integral minus infinity to infinity e raised to minus x square and delta of x plus 1 dx. Here also we have dx, and now we have to find the values of these two integrals. So now to get the values of these two integrals, we'll use an important result from Dirac delta function, that is minus infinity to infinity. If we have here say g of x, and here we have delta of x minus a dx, then this is simply equal to g of a, right? So we calculate the value of this function g of x at x is equal to a, right? So g of a is the value of this integral. So if we take this integral, then g of x is e raised to minus x square, and a is our 1, right? And in the second integral, g of x is again e raised to minus x square, and our a is minus 1, right? So now the value of these two integrals can be written as g of a. So here g of x is e raised to minus x square, a is 1, so here we have g of 1. Then here we have g of minus 1, right? So now we have half, and g of 1 can be obtained by taking here x is equal to 1, so we have e raised to minus 1 square, and here we have e raised to minus, and for x we have minus 1, so we have minus 1 square, right? So this is half, and this is 1 square is 1, so we have e raised to minus 1. Here also we have e raised to minus 1, because minus 1 square is plus, right? So this is half, and this is 2 times e raised to minus 1, and now the value of this integral I is 2, and 2 get cancelled, so we are left with e raised to minus 1, that is 1 over e, right? So viewers, the value of this integral is 1 over e.